half as long. So it would be half the time. This omega here is very much related to my frequency here. I said this was angular speed, but omega is the exact same symbol as the angular frequency. So if we look at frequency as the cycles per second, angular frequency is the radians per second. So one cycle, so back and forth is one cycle. How many radians does the wheel undergo in one cycle?
1 radian.
Not 1 radian. How many radians around this circle?
2.
Oh,
2
if
pi.
you're stopping there, no, pardon?
2 pi.
2 pi. 2 pi. So the relationship between angular frequency and frequency is a factor of 2 pi, and so we have omega, my angular frequency is just 2 pi times the frequency. So in the case of, if my period is 2 pi, so we're looking at the position as the cosine of time. If my period is 2 pi, my frequency is 1 over 2 pi hertz. My angular frequency would be 1 radian per second. If, squeeze it in up here. If my period is now, so I'm looking at the cosine of 2t, my period has been cut in half. So if my period is now pi, because it's half what it was before, that means my frequency is 1 over pi. So my angular frequency is 2 pi times the frequency of 1 over pi, which is just 2. Or in general, that number right there. So I can come up with a generic expression here that my position is equal to the cosine of omega t, where omega is the angular frequency of sort of this hypothetical wheel. I left a little blank in front because we have this amplitude, because I can make it bigger or smaller, vertically, bigger or smaller. And there's one other thing I can do to it, because not everything is going to start at a maximum or at 0. Sometimes, if I were actually doing this in real life, had a motion detector underneath and I was looking at it, I doubt it's going to start at either the amplitude or at 0. So it's going to be slightly off. And so my graph might look like something like that, where there's my peak, but I started a little bit before it. And so we have to somehow account for a shift left or right. And so I introduced the phase shift. So there's my generic equation for position of something undergoing simple harmonic motion. Questions to hear?
Why is it called simple?
Because it goes on forever. Because if you brought in dampening, the fact that it does eventually stop, you now are dealing with a cosine function multiplied by some sort of dampening factor, usually some exponential. And that is not simple. So in comparison. All right, next step. So if I have x is equal to the cosine of 2t, So that's pi, 2 pi. So my graph's looking like that, where that's pi and 2 pi. This is time and this is position. And the first time we did it, it would have looked, oh, I can use for different colors here. The first time we did it, it looked more like this. So if I'm at cosine of 2t, what's that going to do to the slope?
Make it steeper.
Yeah. Matter of fact, it's going to double it. And so whenever I do the slope of a trig function, I have to multiply times whatever number I have in front. So if my position graph is a cosine of omega t plus phi, then my velocity graph is going to be a times omega, negative sine omega t plus phi. And then my acceleration graph will be, well, I'm going to do it again, so I have to multiply by omega again. So negative omega squared cosine omega t plus phi. And now we're ready to plug into our equation of motion. Like that, so I have negative kx is equal to ma. I have my formula for x. Negative a cosine omega t, oops, I lost my k, negative ka omega plus phi equals negative negative m a omega squared cosine omega t plus phi. Well, I have cosine on both sides. I can get rid of it. I can cancel it out, I should say. My amplitude, well, that cancels out also. The negative sign cancels out. And I'm left with, after all that, k is equal to m omega squared. Therefore, omega is equal to the square root of k over m. So from my value for k there, and my mass, which was 0.02 kilograms, I can figure out what my angular frequency is. So I have k of 1.815 newtons per meter. I know my mass was 0.02 kilograms. And so my angular frequency is the square root of 1.815 newtons per meter divided by 0.02 kilograms. And we get somewhere around
9.535.
And units.
Radians.
Say it again.
Radians second.
A second, or per second.
Yes.
Radians per second. So I would expect, given this, that my frequency, therefore, well, I know 2 pi times the frequency is equal to omega. So my frequency would be omega divided by 2 pi, which is 9.535 divided by 2 pi. So we're on 1.5. dividing that? I think you got, did you do 9.535 divided by 2 times pi, or some, however it's on your calculator? If you did that, it's gonna divide by 2, then multiply by pi. You need to make sure there's parentheses around that.
1.518.
1.518 units.
Hertz. Hertz.
I think you just said it.
Hertz.
Yes. Hertz. So the period, therefore, what's the period?
0.659.
Units?
Seconds.
Oh, seconds.
All right. So we have a lot of conclusions here. Let's find out how close we actually get. So what we're gonna do is we're gonna time 10 oscillations of this, see what we get. Timing, so get your timers ready. Three, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
11.88.
11.65.
11.59.
Any others?
11.80.
All right, what do we get as the average?
11.73.
And that's for 10 oscillations, so we divide by 10. So we ended up with an experimental period of 1.173 seconds, which is very different than what we had right there. Why? Why did it not come out? I was not expecting it to come out right, so what's wrong? One of the assumptions we made was invalid. We're going to correct for that, but. The mass, from experience, the mass of a 20 gram mass is going to be somewhere around there, probably off by just a little bit, but not to account for that discrepancy.
Air resistance.
Say it again?
Air resistance.
Ooh, I'm gonna be willing to bet that it's not significant, not that much. Unless there's a reason here I'm not feeling. It's possible, you know, maybe there's nerve damage. All right, what assumptions did we make? Actually, it's, I think, potentially the first assumption we made.
That the wavelength isn't the same. That not the wavelength, that that it's not an ideal spring.
Yes, it is not an ideal spring. In an ideal spring, the spring's massless, but the spring does have mass into it. So we have to figure out what is that effective mass, and that'll help us make our predictions. So what we're gonna do here is sort of work backwards. I know what the experimental period is, and from that I can figure out what the effective mass is. So let's pop off that one. And so I know my period is 1 over my frequency. So the frequency, well, 1.518 hertz. From my frequency, I know that omega is calculated 9.535 radians per second. So all of that part that we did at the end is still valid. This is where it changes. So this is the square root of k over m. That m right there is the mass of, that I added to it, plus the mass of the spring itself. So this would be the square root of 1.815 divided by 0.02 plus the effective mass. So if we squared both sides, 9.535 squared is it 1.815 over 0.02 plus my effective mass. So flip both sides, so I have 0.02 plus my effective mass equals 1.815 divided by 9.535 squared. So let's just at least get that far.
.02.
0.02. They've got another, let's go another decimal point.
0.0199.
Oh, 199?
0.020.
That's what he wrote it.
I rounded because it's
They really rounded it.
0.020.
It's 0.01996.
Okay,
We
all
already
right, so
rounded it
0.0, all right,
0.02.
I understand, sorry about that. All right, so this right here is 0.02?
Yes.
Well, that doesn't seem right.
That's this.
All right, so the period we found, duh. Yeah, it makes sense, it came out to that, so the effective mass is 0 because of the boneheaded error there. I started with our period of 0.659. Of course I'm gonna get an effective mass of 0. That assumed it. No, that's wrong, that's wrong, that's wrong. I'm starting with my experimental period of 1.173 seconds. So my frequency is the reciprocal of that.
.853.
My angular frequency, therefore, that times 2 pi.
.246.
5.246.
Yes.
So that's 5.246. There we go. All right. So 1.815 divided by 5.246 squared.
.00666, yeah.
All right. So my effective mass, therefore, is 0.046 kilograms. So it's effectively, I've got an extra 46 grams hanging on that thing. Let's see how well that matches prediction. I'm gonna take, let's see, I've got a 20 right there. If I do a 50, is that gonna hit the table? Yes. Do we have another 20 somewhere?
What if you swing it around where it's hanging off the table?
Yeah. I think I might have to, I was hoping not to have to move it. $50. Now notice that the amplitude is not part of any of these calculations. All right, so let's figure out what it is experimentally, then we'll figure out what the prediction is, and we will rejoice at how incredible it's gonna be, because this is gonna be the physics demo that works perfectly. All right, people timing? All right. 3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
13.98.
13.85.
13.98, 13.85.
85.
14.19.
14 point what?
19.
19?
14.19.
Okay.
13.88.
All right.